Hello everyone, my name is Chen. I'm a research scientist at Google. So my research interest is on computer vision and machine learning. In the past few years, the field of computer vision has been revolutionized by deep learning. One example is the task of object detection, where the goal is to locate objects with bounding boxes and assign object labels. For video understanding, there is also tremendous progress. Here, I am showing the video classification results from one of the video comnets, and we can see that our video classifier is able to successfully recognize the riding mountain bike action. Besides video classification, there are also many recent work on spatial temporal action detection, where the goal is to locate the actors and recognizing their individual actions. In this example, it will be walking, carrying, and talking. As computer vision is getting increasingly competitive in recognizing atomic concepts such as objects and actions, can we develop algorithms to connect the dots and provide a deeper and richer understanding of the visual world? One such example is human-object interaction, where the goal is to ground the detected actions with interaction objects, such as plates for eating and the listener for listening. We can also treat many tasks in vision and language as an attempt to connect the dots, where one goal is to learn to discover the semantic correspondence between the sentences and the video clips. Finally, many events involve multi-agent interactions, such as sports games, self-driving cars, or even video games. We not only want to recognize and locate the individual agents, but also design tools to allow them interact with each other. All three examples I just mentioned require a structured representation of the visual world. Such representation has clear benefits, such as being interpretable, where one can design a graph structure and associate the nodes and edges with physical entities and their relations. Compared with convolutional neural networks, a structured representation aims at capturing long-term relations, such as entities that are far apart spatially or temporally. Finally, the structured representation enables an object-centric representation, where each agent can be modeled individually, but is allowed to pass messages to other agents. In this talk, I will go over three examples which benefit from the structured representation. They are multimodal relations, unsupervised tracking and prediction, and also multi-agent behavior prediction. I will start with the multimodal representation. Our motivation is that many people upload the so-called instruction videos to the internet, and they use cameras to capture what they are doing, and pair with useful narrations that are closely related to the visual content. Thanks to platforms such as YouTube or TikTok, the content is abundant and up-to-date. The question then becomes, how can we distill this useful information from these unlabeled videos? Let's first take a look at what we have from these videos. We have the frames and audio signals that are temporally aligned. We can also apply an off-the-shelf ASR algorithm to convert the audio into the text. We then want to establish the cross-modal dependencies between visual and language input. In this example, it will be between the middle video clip and the description moving around your kickboard. We are also interested in temporal dependencies on how human activities unfold over time. Both cross-modal and temporal dependencies are long-term dependencies, which can be established between nodes that are far away from each other in the sequence. What would be good tools to model such long-term dependencies? One option is to use recurrent neural networks. Given sequential observations X, it recurrently updates the hidden state H based on the current observation and the hidden states of the previous step. However, It is known that it is challenging for a vanilla recurrent neural network to model long sequences. Also, it requires us to define an ordering which does not exist in cross-model case. We can also use 1D convolutions, which frees us from defining the order. However, the convolution operation has a fixed kernel size which limits its receptive field. In this case, it will be only 3. More recently, the self-attention operation has been shown very powerful for natural language processing. It's trying to learn a linear combination of all widget inputs in the sequence based on some learned similarity metric. You can imagine it as a fully connected graph with learned edge weights. And we are doing message passing among the nodes. This gives unlimited receptive field. If the self-attention is extended to the multi-headed case, it is also at least as expressive as convolution operations. In this work, we use multi-headed self-attention as the basic module. Now that we have the self-attention operation to model dependencies, what would be a proper training objective to learn the cross-modal and temporal dependencies? We seek inspiration from the natural language processing community on how they model the sequence dependencies. One simple yet powerful training objective, as popularized by the Bird paper in 2019, is to predict missing words that are randomly masked out in the text sequence. In this example, in order to predict the word cute, our humans need to look at relevant words such as dog, likes, and play. So we can see that this training objective encouraged the model to capture semantic dependencies. For videos, we hope to do something similar. Here I'm showing 6 video clips in a cooking video, ordered by time. We want to mask out, for example, the third clip, and ask the model to predict the missing clip. However, unlike predicting words, it is unclear how to define the loss function for video pixels. Our first option is to apply a perceptual loss, where one can apply their favorite generative model, such as a variational autoencoder or a generative adversarial network, to directly predict the pixels. We can then compare the generated pixels with ground truths, for example, by doing maximum likelihood training. However, although there are huge progress in deep generative models, it is known that generating pixels is challenging for unconstrained videos. Besides, for the purpose of learning cross-modal and temporal dependencies, chances are that we don't care about the subtle details, such as the layout of the kitchen or the color of the person's shirt. All we care about is the action heating chocolate. And these 3 clips, although their visual appearances are quite different, they should be considered as equally good, meaning that it's not necessary to reconstruct the subtle details. Instead, we define a loss function based on high-level semantics. For each of the video clip, we apply a pre-trained deep neural network to extract the visual features. We then use hierarchical k-means to group different video clips into clusters. Our hope is that semantically close videos are grouped into the same clusters. We call this clustering step as tokenization. Here are some of the visualizations of the tokenization outputs. Each row corresponds to a video. On the left, I show the keyframes for the original videos. One is decorating a cake, the other is spreading butter on bread. On the right are the visualizations after the tokenization step. For each frame, I show the image closest to the cluster centroids, so they could come from different videos in the training dataset. We can see that the subtle details, such as the color of the outfits, are different. However, the high-level semantics, such as cakes, cake boards, and moving around the cake board, are preserved after the tokenization step. Here is the overview of our proposed framework. The inputs are tokenized video clips and outputs of ASR's system. that are temporally aligned. Some of the inputs are randomly masked out, and we pass them to the stack self-attention layers. We name the overall framework as WidowBird. Here is a more detailed view on the inputs and target outputs of WidowBird. Given input corpus, we can either keep the video intact and mask out the words, which is a way to learn object classifiers. Or we can mask out the video clips and ask the model to predict based on the language. We can also use video-only inputs, and ask the model to learn temporal dynamics. Here is our experimental setup. For training, we use around 1 million instruction videos on YouTube. They cover a wide range of topics such as cooking, gardening, and even fixing cars. We run off-the-shelf ASR system to get noisy speech annotations with timestamps. None of the training videos are manually annotated. For evaluation, we choose several standard academic benchmarks that are human annotated with clean labels. And it is worth noting that the only video frames are used. Our algorithms do not require the videos for evaluation to have audio tracks. Okay, now once the model is trained, we first conduct some qualitative analysis. Here, we ask the model to perform the task of recipe illustration. Each row corresponds to 4 steps of some written recipe. We ask WidowBird model to condition on the input text and predict one missing video token. We then visualize the video token using the keyframes that are nearest to the cluster centroids. We can see that the resulting video predictions are pretty high quality. Because of the hierarchical k-means operations, the retrieved keyframes could come from different videos. However, they are nicely aligned with the text recipe in the semantic space. A future work could be to train a video generator with consistent appearance over time from these retrieved latent video features. Another qualitative analysis would be to see if WidowBird is able to generate realistic features. Here, we are providing a bowl of cocoa powder and bowl of egg and flour to the WidowBird model, and ask it to retrieve the tokens at different future timestamps. We can see that for the bowl of cocoa powder, our model first predict it will be turned and put into oven, and then predict it might be transformed into a brownie or a cupcake. For the second example, if the model predicts that the mixture will be put into a frying pan. Finally, we conduct some quantitative analysis. We took a cooking video dataset named ucook2 and performs the zero-shot classification task. Zero-shot here means that we do not know the categories beforehand and directly use the model to predict the objects and actions conditioned on the video inputs. On the right, we show the zero-shot classification accuracy as a function of pre-training data size. We can see that as more videos are used for training, the accuracy keeps going up, and given enough data, it even surpasses the fully supervised baseline. The supervised baseline knows the classification categories and was trained on the training split of the cooking dataset. So our zero-shot performance was quite competitive. Now let's move on to the second example, where we aim at discovering object structures and use them for tracking and prediction. I guess most of you are familiar with this Johansson experiment in 1973. Although we are only provided a set of moving dots, it is easy for us humans to recognize that there are likely to be 2 persons. The left is doing some hand gestures, and the right is walking. The experiment demonstrates that we are able to recover human actions from moving key points. A natural question to ask is then, can we go the other way and discover these structured key points from actions in videos? You might be wondering why we don't use the standard supervised learning techniques, which have been shown very powerful for key point detections. Indeed, in the example on the left, I'm showing a demo from Google on hand keypoint detection, trained on a large amount of labeled images. We can see that the results are very reliable. However, there are many scenarios, such as robot grasping on the right, that it is unclear how to define the key points, for example, for a glove or for a marker pen. It is thus desirable to discover these key points purely in a data-driven or goal-driven manner. As the only available inputs are video frames, let's first take a look at what might happen if we resort to the image reconstruction objective. Here, I am showing a standard autoencoder where the inputs and outputs are both neural networks. And a bottleneck is a feature vector. It is easy for us to see that the bottleneck is not interpretable, and it can choose to encode any information it wants to, such as appearance information or motion information. Alternatively, you can ask the encoder to predict the key point locations in 2D coordinates. However, to make sure that these key points are indeed semantically meaningful, we need to add two important constraints. First, we want to constrain only key point information is stored in the bottleneck. So we need to provide a reference from T0, which provides appearance information about the object and the background. Second, we need to make sure that the 2D coordinates are interpreted properly. For this goal, we render the 2D coordinates as Gaussian blobs on an image and concatenate with the reference frame channel-wise. We also use a deconvolutional network for the decoder, and its inductive bias forces the decoder to respect the spatial locality of the key points. By restricting the bottleneck only contains 2D coordinates and reconstructing source frame from a reference frame, it encourages the model to detect key points that are invariant to viewpoint changes. We can also take one step further and train a recurrent neural network to predict how the coordinates might move to the future timestamps. Instead of reconstructing the input at T1, we can then reconstruct the unseen future frames at T2, T3, etc. And this is our overall framework. You can see that by generating the future pixels, the key points are not only invariant to viewpoint changes, but also encouraged to have robust temporal dynamics, which can be captured by our dynamics model. This basically allows us to train a generative model of video pixels with the desirable side effect of discovering object key points and trackers. No manual definition of the key points where annotations of the key points are needed in this process. We can imagine that there are multiple possible futures given the same observed video frames. To handle this, we use the variational RNN to achieve stochastic prediction of future dynamics. A recurrent neural network is deterministic, and it uses a fixed function to update the hidden states H. Here, we inject stochasticity by adding a latent variable Z. We can treat the Z as a latent intent variable encoding the state of the mind of the agent. During inference time, we can sample the latent intents from a distribution so that the model can generate diverse futures. Here are some qualitative results. We train and evaluate our model on the human 3.6 million dataset, which has different actors performing different actions before a fixed camera. The first row I'm showing is the input video, and the first two frames in green are given as input to the model. The second row shows the detected key points and their trajectories, and the third row shows the reconstructed images. There are two observations here. First, we can see that the key points correlated well with the human joints, although now fall on the background. Although some of them fall in the background, the trajectories are relatively stable. Second, you can see that the predicted trajectory is different from the ground truth, especially after 20 frames, but the generated results is totally plausible. Another interesting observation is that since the reference frame does not provide the back of the person, the model basically imagines the back is in gray. Since the key points are unsupervised, we need to map them into human-defined key points for evaluation purpose. And we just train a very simple linear regressor to achieve this goal. Here are the comparisons with some non-structured baseline approaches. Only the first second is observed for all the baseline models and our proposed method, and the following are predicted trajectories. Because there are multiple features, for each baseline we run multiple samples. The main observation is that our performance in red curve is almost as good as the supervised version. And because our discovered key points are optimized for the dynamics, for time t bigger than 4, it even outperforms the supervised version. Here, I'm also showing the video prediction results. Each column is a different sample. First row is ground truth. Second row is a previous safety art. Third row is our method. And the final row is without structure bottleneck. We can see that by using a structured representation and modeling temporal dynamics in the structure space, our method is able to generate stable video predictions for long time horizon. The baseline methods are blurring. We can see that our model is also able to generate diverse samples. Because our representation is interpretable, we can directly manipulate the key points and conduct condition generation by stretching different body parts. Finally, we also apply our method on the DeepMind reinforcement learning suite. And here are some of the generations results of action condition generation for in this environment. Our goal is to predict the action condition reward by using this dynamics model, which can then be used to improve reinforcement learning policies. We can see that our structure model consistently uses lower error than the non-structure model. Finally, I will discuss how a structured representation can help multi-agent systems. The specific task we are interested in is vehicle behavior prediction, where the inputs are detected vehicle trajectories and the scene context, such as road maps. And the outputs are possible trajectories for all vehicles in the next 3 to 5 seconds. The task is important for self-driving cars to plan ahead and makes the safest possible decisions. I like this task as it perfectly complements the previous example. In the previous example, we want to discover object structures such as key points automatically from the raw video inputs. Here, we are trying to solve a reverse problem. We are provided with rich, structured scene context metadata that is highly detailed maps, which includes maybe the layout of the road and the traffic rules and traffic lights. And our problem now becomes how to properly and effectively use these scene structures. Most previously methods on behavior or intent prediction adapts a non-structured representation of these high detailed maps. They render the maps into top-down view, color-coded images, as shown in the example below, and then encode the rendered map with convnets. However, there are several limitations with this approach. First, convnets are not designed to capture long-range structures, which are important for behavior prediction if we want to plan 3 or 5 seconds ahead. Second, it is often unnatural to map structure metadata into color-coded images. It might lead to missing information or some ambiguity. Finally, from an application perspective, the rendering step and the convnets could be memory consuming and computationally intensive. Now, let's take a look at what's inside an HD map. There are points, such as traffic lights. There are polygons, such as crosswalks. And also there are curves, such as line boundaries. It is worth noting that the vehicle trajectories can also be represented as those curves. All these elements can be approximated with polylines, which themselves are a collection of vectors associated with properties such as the 3D coordinates and optionally timestamps. This motivates us to propose VectorNet, which is a structured representation of both scene context and vehicle dynamics. The inputs to VectorNet are the polylines from both the HD map and also the vehicle trajectories. Each polyline is represented by a collection of vectors. The polyline group ID and other state information, such as whether it's a lane boundary or vehicle trajectory, or the color of the traffic lights. These inputs are then fed into a hierarchical graph neural network. In the first level of the network, which is composed of the polyline subgraphs, VectorNet gathers information within each polyline, such as local road geometry and vehicle dynamics. In the second level, which is called global interaction graph, VectorNet exchanges information among polylines, such as how to follow the lanes or when to yield to other vehicles. VectorNet is optimized with two training objectives. The first one is the standard target vehicle trajectory loss function, such as the Huber loss between the ground truth future trajectories and the predicted future trajectories. We also add an auxiliary loss where we randomly mask out a subset of the node features in the global interaction graph and ask the model to complete the masked node features. The goal is to encourage VectorNet to capture useful relations between all elements in the graph. We apply VectorNet on two behavior prediction benchmarks. One is an internal benchmark from Waymo. The other is a public benchmark from Argoverse. We compare VectorNet with a ResNet 18 encoder applied on rendered maps. We can see that VectorNet achieves lower displacement error with significantly fewer flop and parameter counts. For more comparisons and ablation studies, please refer to our paper. Here we present a few visualizations to see why VectorNet achieves better performance. Here is an example for a lane change. On the left, we show the map in gray, the non-target vehicles in green, and the ground truth future in purple, and finally the predicted future in blue. On the right, we highlight the polylines that receive the highest graph attention in red. We can see that the VectorNet is able to identify the most important contexts, which are the current and target lanes in this example. We can also see that the relevant context could be far away from the target location, a target vehicle location. Here is another example at a traffic intersection. The vehicle decides to go straight, but to reach this prediction, VectorNet actually attends to all possible alternatives, such as turning left and turning right. Okay, here is a brief summary of the talk. We went over 3 examples on structured representations of the visual world. We can see that they are interpretable, such as providing visual linguistic correspondences and discover object structures. They are good at capturing non-local spatial, temporal, or cross-modal relations. And finally, it provides a natural inductive bias for multi-agent systems. Finally, I would like to share a personal thought that graphs provide a way to approach perception problems in a structured way. They are not tied to any particular architecture, and many architectures can be treated as graphs. Thank you.